Hi everyone. As I mentioned during our meeting on Monday, this is probably the single most important video of the semester because it's going to explain how exactly inferential statistics work. In today's video, we're going to go through the process of how inferential statistics work, and for the rest of the semester, all we're really going to do is repeat that same exact process over and over again in slightly different ways. So if you understand the stuff in today's video, the rest of the semester will be a breeze for you. The first thing I want to do is just quickly recap what we talked about at the end of Monday's class. We talked about how to write a good hypothesis. Remember that a hypothesis is a statement, not a question, that predicts either a difference between groups or a relationship between two variables. So for example, we might hypothesize that there is a relationship between height and weight, that people who are taller tend to weigh more. We could also hypothesize that men and women are different in terms of the number of pairs of shoes that they own, one of the questions that you answered in your class survey. Each of those would be an example of a good hypothesis. Again, what makes a good hypothesis is that it's a statement, not a question, and it should define the thing that we're measuring. So it should include the operational definitions of our variables. We talked also briefly about how a hypothesis can be either directional, meaning we're being specific about the nature of the relationship, or non-directional, meaning we're not being specific. We're just saying there's going to be a difference or a relationship, but we're not describing what we think that difference or relationship will look like. Most importantly for today, to set the stage for what we're going to talk about in the rest of this video, when we are testing a hypothesis in statistics, what we're actually doing is we're testing two competing hypotheses. On Monday, we talked about the null hypothesis, which we abbreviate as H with a little O next to it. The null hypothesis always says that there is no difference between the groups that we're comparing, or there is no relationship between the variables that we're interested in. The opposite of the null hypothesis is the alternative hypothesis, which is always going to say that there is a difference between the groups that we're comparing, or there is a relationship between the variables that we're looking at. Now, by definition, one of these two things has to be true, and one of these two things has to be wrong. There either is a difference or relationship, or there isn't one. What we're going to talk about in today's video, and what we're going to do for the rest of the semester, is figure out how exactly do we decide which of these two hypotheses we think is right and which of these two hypotheses we think is wrong. In general terms, what we're going to do is we're going to calculate a statistic that tells us something about the strength of the evidence. How strong is the evidence that we have a difference or a relationship in the data? If we find that the evidence of a difference or relationship is only weak, we are going to do what's called retain the null hypothesis. In other words, we are rejecting the alternative hypothesis. We are saying we think the null hypothesis is correct. In that case, our conclusion will be that there is no difference or no relationship because we have not found good evidence that there is one. If, however, we find that the evidence of a difference or relationship is strong, we are going to reject the null hypothesis, and we are going to go with the alternative hypothesis as the one that we think is correct. So in that situation, if we find strong evidence of a difference or relationship, that's going to be our conclusion, is that there really is a difference. These groups really are different, or these variables really are related. Now, you're probably wondering, how exactly do we know whether the evidence is weak or strong? And we're going to get to that in just a second. First, let's make this more concrete by putting it to an example. Let's say I wanted to know whether there was a difference between the exam scores of the men and the women in this class. Remember, the null hypothesis always says that there's no difference or no relationship. So we could phrase the null hypothesis here as there is no relationship between sex, meaning male versus female, and exam score. Or we could phrase the null hypothesis as there is no difference between the exam scores of men and the exam scores of women. The alternative hypothesis here is the opposite of that, that there is a relationship between sex and exam score, or in other words, we could phrase the alternative hypothesis as there is a difference between the exam scores of men and the exam scores of women. Now, if we wanted to test this hypothesis, I could give you all an exam. I would calculate the average score for men. I would calculate the average score for women. And I would use an inferential statistic to compare the exam scores of men and women. That inferential statistic is going to tell me one of two things. It might tell me that there is only weak evidence of a relationship between sex and exam score. If that's the case, I'm going to retain the null hypothesis, and my conclusion will be, based on the evidence I have, men's and women's exam scores were not different. In other words, the null hypothesis is the one that I think is correct. If, however, that inferential statistic tells me that there is strong evidence of a relationship between sex and exam score, I'm going to reject the null hypothesis, and my conclusion is going to be that I think the alternative hypothesis is the one that is correct. In other words, my conclusion will be that men's and women's exam scores were, in fact, different. Now again, the elephant in the room here is, how do we know if the evidence is weak or strong? That the whole process of inferential statistics depends on that decision. We have to pick one of these two hypotheses as correct and the other one is incorrect. How are we going to make that decision? To illustrate how these tests work, what we're going to do now is we're going to play a game together. So here's how this game is going to work. I have here a deck of playing cards. Now, if we were doing this in class, what I would do is I would walk around the room and I would solicit volunteers to draw a card from the deck. Since we can't do that, I will draw the cards for you. Now, it's a very easy game. The first person who draws a black card from the deck, so the first person who draws either a spade or a club rather than a heart or a diamond, will win a prize. Now, if we were doing this in person, the prize that you would win would be a candy bar. But unfortunately, I can't really give you a candy bar through Zoom. But I think I've come up with something better. The first person who draws a black card from the deck will win the right to drop the 2 lowest homeworks from their final grade. So everybody gets to drop their lowest homework. This person, and only this person who wins this game, will be able to drop their 2 lowest homeworks. Now, to make this fair, what I've done, and I'm going to share my screen right now, is I've taken all of your names and I've randomized them. So these are everybody in the class in random order. What we're going to do is we're just going to go straight down the list. I'm going to draw from the top of the deck, and the first person to get a black card wins. Pretty easy, right? Okay, so our first contestant is going to be Devin. Devin, your card is, what is that? The 10 of diamonds. Sorry, Devin, today is not your lucky day. So we're going to go ahead and put in here that Devin drew the 10 of diamonds. I'm going to make that red just so we all know that that was a red card. Okay, I'm going to go ahead and put the 10 of diamonds at the bottom of the deck. Our next contestant is going to be Marcus. Marcus's card is, sorry, Marcus, it is the Queen of Diamonds, another red card. So Marcus, you too have lost the game. Sorry about that. Maybe Katya will have better luck. I'm going to take Marcus's card, put it at the bottom of the deck. I will draw Katya's card from the top. Katya, it would be nice if we could win here, and we did not. 2 of hearts was Katya's card. So here we go, 2 of hearts. Make that red. Okay, that's a little strange, but let's keep going. I put Katya's 2 of hearts at the bottom of the deck. I will now draw a card for our next contestant, who will be Rachel. Rachel's card is the 5 of diamonds. Damn. Okay, well, 4 contestants, 4 losers so far. Well, we know there's black cards in this deck, so we got to win eventually. Our next contestant is going to be Michaela. I've put Rachel's card at the bottom of the deck. Michaela, your card is... Oh my god, the 4 of diamonds. Okay, we are yet to have a winner. The 4 of diamonds. Let's keep going. Rebecca, it would be nice if you could end this so we could move on with the rest of the video. Rebecca, your card is... Oh my god. The Queen of Hearts. Yet another red card. My god. Okay. Rebecca, you also have lost the game. Sorry. Better luck next time. Rebecca's card is now at the bottom of the deck. All right, let's get a black card and end this. Jasmine, your card is the 2 of diamonds. My goodness. Okay. 2 of diamonds. We've now gotten 7 red cards in a row. Holy crap. Okay, let's keep going. Maybe we got to get a black card eventually. Okay, Stephanie, you are our next contestant. And your card, oh my god. Your card is the 7 of diamonds. Okay. Oh boy. What should we do? Should we keep going? I guess we should keep going. We got to keep going until somebody wins. Okay. So Arlene, your card is now at the bottom of the deck. I'm sorry, Stephanie's card is at the bottom of the deck. Arlene, your card is going to be the one at the top of the deck. Oh boy. Okay. Which is the 9 of hearts. That is now 9 red cards in a row. Boy. Okay. Hopefully this will end soon. Okay. Arlene, I've put your card at the bottom of the deck. Beyonce, our 10th contestant. Beyonce, your card is the Jack of Hearts. Oh my god. Okay. That's now 10 red cards in a row. That's really weird. Okay. Now, if we were doing this in person, at this point I would say, well, do we want to keep going? I mean, nobody's won. We've done this 10 times. Frankly, I'm kind of surprised that nobody's won because there's 26 black cards and 26 red cards in a deck. So we probably should have drawn a black card by now. We maybe just are extremely unlucky here. Should we keep going? I mean, should we do a couple more? Let's try one more. Aaron, you're going to be our next contestant. Aaron's card is the 8 of hearts. Wow. Okay. Nobody clearly wants to win this, so I think we're just going to stop the game here. Wow. Now, is anybody skeptical of what just happened? If we were doing this in person, I'd be willing to bet that some of you at this point would be accusing me of cheating. Even though, you know, I've never lied to you before. You have no reason to believe that I would lie to you, but maybe you do now. The reason for that is that what just happened, drawing 11 red cards in a row from a deck of cards, it is technically possible, right? Because there's 26 red cards and there's 26 black cards in a deck of cards. So it is technically possible to draw 11 red cards in a row. However, we also know that it is extremely unlikely for that to happen. If this is in fact a normal deck of cards with 26 black and 26 red, it would be really, really strange for there to be 11 red cards in a row at the top of the deck. It's possible, but it would be really, really unusual. So all of you are probably wondering right now, what is going on here? One possibility is that we just got extremely unlucky. We happen to be that one person in a million who drew 11 red cards in a row from the top of a normal deck of cards. That's one possibility. The other possibility is maybe this isn't a normal deck of cards, right? Maybe some of you are thinking, he's messing with us. That's not a normal deck of cards. Because if this were a normal deck of cards, what just happened is really, really weird. If you follow my logic here, you follow the logic of inferential statistics. That's exactly how inferential statistics works. When we get evidence, right, what we just did is we essentially collected data from 11 people. And we found that all 11 of those people drew red cards. So we have to decide between two possible explanations here. One possible explanation is that we just got extremely unlucky, and this is in fact a normal deck of cards. The other possibility is that this isn't a normal deck of cards. Now, as we were going through this, each of you probably at some point started to get skeptical, right? When the first person, Devin, drew a red card, you probably thought, okay, Devin just got unlucky. She had a 50-50 shot. She didn't win. Then Marcus also drew a red card, and you probably thought, okay, he also got unlucky. 2 red cards in a row, not a big deal. But then we drew a third one, and a fourth one, and a fifth one, and a sixth one. And at some point, I bet each and every one of you thought, wait a minute, something weird is going on here. This doesn't make sense. If this was a normal deck of cards, we would have drawn a black card by now, because that's how probability works, right? And some of you might have started to get skeptical after 4 red cards in a row. Some of you might have started to get skeptical after 6 or after 8 or even after 10. But I bet every one of you at some point said, wait a minute, based on what just happened, based on the evidence, the data that we just collected, I don't think this is a normal deck of cards anymore. That's exactly how inferential statistics works. Let me explain further. When I first pulled out the deck of cards, you had no reason to believe that it was anything other than a normal deck of cards, that half the cards were red and half the cards were black. That was like your null hypothesis. So your null hypothesis here was that the number of red cards was equal to, or in other words, not different from, the number of black cards in the deck. Then we went and collected some data. We drew a red card, no big deal. We drew a second red card, okay. We drew a third red card, that's kind of weird. We drew a fourth red card, okay, that's starting to get kind of strange. We drew a fifth red card. And as I mentioned a minute ago, at some point, I bet each of you said, this is too weird to be true. This must not be a normal deck of cards, because if this was a normal deck of cards, what just happened is really, really strange. If you look under each of these cards on the screen, it actually tells us the actual probability. So the probability of drawing 1 red card in a row is 50%, right? It's a 50-50 shot. And then every subsequent red card, that probability gets cut in half. So the probability of drawing 2 red cards in a row from a normal deck of cards is 25%. The probability of drawing 3 red cards in a row from a normal deck of cards is 12.5%, and so on and so on and so on. So every time we drew another red card, the pattern that we were seeing got stranger and stranger and stranger. And it probably led you to think, well, maybe this isn't a normal deck of cards. So at some point you had to make a decision. Either this is a normal deck of cards or it isn't. In other words, you all thought to yourselves, if in fact this is a normal deck of cards, then what just happened is really, really unlikely to happen. It's not impossible, but it's really, really unlikely to happen. So one of two things has to be happening here. Either we just got extremely unlucky, or this isn't a normal deck of cards. Now, as we'll talk about later today, we are never going to be 100% sure that we made the right decision, right? But in this case, the evidence is probably making you lean very strongly in one direction rather than the other. And what you're probably all thinking, whether it took you 4 or 6 or 8 or 10 cards to come to this conclusion, you're probably all thinking, well, based on what just happened, I actually don't think this is a normal deck of cards. I think more than half of those cards are red. Maybe all of those cards are red. In other words, what you just did is you started with a null hypothesis. And your null hypothesis was that the number of red cards was not different from the number of black cards. Then you collected some data, and based on what you saw in those data, you said, well, wait a minute, I think my null hypothesis might be wrong. I don't think the number of red cards is actually equal to the number of black cards. I think, based on what I just saw from the deck, I think that there's more red cards than black cards, that the number of red cards is larger than the number of black cards. So what you all did at some point is you rejected that null hypothesis and you said, you know what, I think this is wrong. I don't think this is a normal deck of cards. I'm going to say the alternative hypothesis here is correct, that the number of red cards is not the same as the number of black cards. But again, we don't know if you were right. Maybe we were just that 1 in a million person who got it wrong. Now, this tells us about how we make decisions about which of the two hypotheses we're going to go with. We have to make a decision about whether we think the null hypothesis is correct or the alternative hypothesis is correct. And the way that we do that is by using probability, specifically using a number called a p-value. P standing for probability. For the entire rest of the semester, we are going to learn a bunch of different types of inferential statistics, but they all have one thing in common, which is they are all going to give us what's called a p-value. And the p-value is going to be the single number that tells us which of the two hypotheses we think is more likely to be correct. Now here's the textbook definition of what a p-value is. A p-value is the probability of getting results or getting data that are at least as extreme as the results we got if the null hypothesis is true. So in the context of the game that we just played, the p-value would be, for example, if this is a normal deck of cards, what is the probability of drawing 5 or more red cards in a row, or 6 or more red cards in a row, or 7 or more red cards in a row? So every time we drew another red card, the p-value, the probability of that happening, gets smaller and smaller and smaller. It never is 0, right? We could technically draw 11 red cards in a row from a normal deck of cards. It's not impossible, but it's extremely unlikely to happen. So in other words, the p-value, the probability of that happening, would be a very, very, very small number. Here's how we're going to interpret the value of p whenever we do an inferential statistic. If p is a large number, what that's telling us is that the results that we got were not that strange. They were not that improbable. And therefore, it doesn't provide strong evidence against the null hypothesis. For example, drawing 2 red cards in a row is not a big deal, right? I bet very few of you, if any of you, started to get suspicious after we drew only 2 red cards, because it's not that unlikely to happen. So if we had stopped the game after the first 2 cards, you probably would not have been suspicious that this wasn't a normal deck of cards, because that happens all the time. However, if our p-value is very small, what that's telling us is that the results that we got are very odd, very improbable. And that means that they provide strong evidence against the null hypothesis. So whereas drawing only 2 red cards in a row is weak evidence, drawing, say, 10 red cards in a row is strong evidence. It's very improbable. It's very unusual that that would happen if, in fact, this is a normal deck of cards. So once we draw 10 red cards in a row, you might be convinced at that point, this can't possibly be a normal deck of cards. Now, it could, but you know, it's very, very unlikely. But we still haven't quite answered our question. We know that if the p-value is large, that's telling us that the evidence is weak. And if the p-value is small, that means the evidence is strong. But how exactly are we going to define large and small? Remember from our discussion of z-scores that people who are unusual are found in the tails of the distribution, right? So people who are unusually tall or unusually short, for example, or people who slept for 12 hours or people who slept for only 4 hours, people who are very unusual. The way that we interpret a p-value is going to be very similar. So the value of p is always going to be somewhere between 0 and 1. Always. The more unusual the outcome, the smaller the p-value gets, right? So if we draw one red card in a row, the likelihood of that happening in a normal deck of cards is 50%. So our p-value there would be 0.5. It happens half of the time. The probability of drawing 2 red cards in a row from a normal deck of cards is 25%, which would correspond to a p-value of 0.25. We have to decide at what point are we convinced? At what point do we think that the evidence is strong enough that we're going to reject the null hypothesis and go with the alternative hypothesis instead? We have to draw the line somewhere. That place where we decide to draw the line is called the alpha level. So the alpha level is our determination of how strong does the evidence have to be, how small does the p-value have to be in order for us to be convinced that the null hypothesis isn't true. Now, in science and in statistics, it is widely agreed upon that the cutoff is going to be 5%, or in other words, 0.05. There's nothing special about that number other than the fact that scientists all kind of agree that that's a good number to use. In other words, scientists are all kind of agreeing that we're comfortable being wrong as long as we're only wrong less than 5% of the time. That is going to be our cutoff. So, anytime we get a p-value, and that p-value is larger than 0.05, in other words, that p-value is somewhere between. In our card game example, for example, drawing 2 red cards in a row is not very unusual, right? It would probably be right about here in the curve, right in the middle. But as we drew more and more and more red cards, that became more and more and more unusual. So we moved away from the middle of the curve toward the tails. And at some point, we crossed this threshold where instead of thinking it was a normal deck of cards, the evidence became so compelling, so unusual, that we decided we were going to reject the null hypothesis and instead believe that this was not, in fact, a normal deck of cards. A very important concept in statistics is a concept called significance. Now, I'm sure everybody in here has heard the word significant before, and here's the dictionary definition of significant. You probably think of the word significant as being synonymous with big or important or meaningful, but in statistics, it doesn't mean any of those things. In statistics, the word significant has a very specific meaning, which is that it is unlikely to be due to chance. Significant means that it is unlikely to be due to chance. So if we reject the null hypothesis, another way of saying that is that we have found a significant relationship between the variables we were interested in, or we have found a significant difference between the groups that we were comparing. Significant is only used to describe situations where we find a p-value of less than 0.05, meaning we reject the null hypothesis. We would refer to that as a significant difference or a significant relationship. doesn't necessarily mean that it's large or important, but it does mean that it is very unlikely to have happened just by dumb luck. So let's quickly summarize to this point. Every time we run an inferential test, we are going to get a p-value. We are going to look at that p-value and we are going to ask ourselves, is this number greater than 0.05 or less than 0.05? It's always going to be one of those two things. If we find a p-value of greater than 0.05, this would be the equivalent of drawing, say, only 2 red cards in a row. That tells us that the evidence against the null hypothesis, in other words, the evidence of a difference or relationship, is weak. So these results are probably just due to random chance, right? Drawing 2 red cards in a row just by dumb luck is not a big deal. So we are going to retain the null hypothesis in that case, and we are going to conclude that there is no significant difference or no significant relationship. If, however, our p-value is less than 0.05, that tells us that we have strong evidence against the null hypothesis, and that the results that we got are very unlikely to happen if the null hypothesis is true. So this is the equivalent of drawing 7, 8, 9, or 10 red cards in a row. If we find evidence that's that compelling, we are going to reject the null hypothesis, and our conclusion is going to be that there is a significant difference or relationship. Okay, this will be the last bit for today's video. Because we are using probability to make our decision about whether we're going to reject or retain the null hypothesis, there's always a chance, even a very small chance, that we made the wrong decision. We can choose, based on the data that we have and based on the p-value, we're going to choose to either retain or reject the null hypothesis. Now, in actuality, the null hypothesis is either true, meaning there actually isn't a difference or relationship, or the null hypothesis is actually false, meaning there actually is a difference or relationship. The problem is, we don't know for sure whether the null hypothesis is actually true or actually false. But let's pretend for a second that we could know that we had some way of knowing for sure if the null hypothesis was true or not. If we choose to retain the null hypothesis, and it turns out that the null hypothesis actually was true, there really wasn't a difference, we made the right choice, right? We said, I don't think there's a relationship, and in fact, there wasn't a relationship. We would call that a correct retention. If, however, we decide that there is a relationship, that the null hypothesis is false, and it turns out the null hypothesis actually was false, we again made a correct decision, right? We said, I think there is a difference or a relationship, and in fact, there was. We would call that a correct rejection. However, there's also 2 different kinds of mistakes we could make here. What if we said, I think that there is a relationship, but there actually wasn't one? We rejected the null hypothesis, but we actually shouldn't have, because it was true. In statistics, we call that a type 1 error. We concluded that there was a difference or relationship, but in fact, we were wrong. As I mentioned before, it is possible to draw 11 red cards in a row from a normal deck of cards. It's possible. And you don't know for a fact that the deck of cards that I was using earlier is not a normal deck of cards. So if I were to show you that deck of cards and you saw that it actually was a normal deck of cards, you would have committed a type 1 error here. You would have concluded, I don't think this is a normal deck of cards, but then it turns out it actually was. We can also commit the opposite type of error. If we choose to retain the null hypothesis, we conclude that there was no difference, but it turns out there actually was one. We call that a type 2 error. This usually happens because we didn't collect enough data, right? There was a difference or there was a relationship, but we failed to find it. We didn't see it because we didn't have enough information. So if, for example, if we had stopped the game after only 2 cards, and you had said, yeah, you know what? I think this is still a normal deck of cards, you would have been wrong. You would have committed a type 2 error. Here's a little graphic that kind of reiterates those 2 types of errors. So a type 1 error is sometimes called a false positive. So if a doctor told the man on the left that he was pregnant, that would be a mistake, right? I'm concluding that you are pregnant, but in fact you are not. That is a false positive or a type 1 error. If the doctor on the left side of the screen told the woman she was not pregnant, that would be a type 2 error. She's concluding that there is no pregnancy when in fact there was one. And that's also called a false negative. If you're familiar with the story, The Boy Who Cried Wolf, which you probably heard growing up at some point, the people who live in the town commit both type 1 and type 2 errors. So just for those who might be unfamiliar with the story, what happens in the story is a boy is charged with guarding sheep from a wolf, and the boy would always say that the wolf was here, and the people would panic, and then the boy was, lying. And the boy would say the wolf is here, people would panic, boy was lying, and so on and so on and so on. Until the end of the story, when the boy says the wolf is there and no one believes him. And then the wolf actually is there. So first, the people in this story commit several type 1 errors, right? You can think of the boy in this story as being like your p-value or your inferential statistic. So the boy is saying the wolf is here, and the people are freaking out, and then turns out they were wrong. False positive error. And they do that again and again and again. And then at the end of the story, they think the wolf isn't there, but it turns out the wolf really is there. They committed a false negative error. So the last slide here, let's tie together everything that we've talked about today and make it concrete in the same example that we were talking about in class on Monday. We talked about a hypothetical study where we have half of the students in the class take notes by hand and half of the students take notes on a computer. And at the end of the semester, we compare the final exam scores of the students who took notes by hand against the students who took notes on a computer. Our null hypothesis always says that there is no difference or no relationship. So in this case, our null hypothesis might say there is no relationship between how you take notes and the score you get on an exam. A different way of phrasing that null hypothesis would be that there is no difference between the exam scores of students who take notes by hand versus the exam scores of students who take notes on a computer. The alternative hypothesis is just the opposite of that. It would say that there is a relationship between how you take notes and your score on the exam, or that there is a difference between the two groups of students in terms of how they how well they do on the exam. Now, if we wanted to actually do this study, we could do it, right? We could ask half of the class to take notes by hand, half take notes on a laptop. At the end of the semester, I would calculate the average exam scores for each group, and I could compare them against each other using an inferential statistic or an inferential test. Now, what we're going to do for the rest of the semester is we're going to learn a bunch of different inferential tests. But the reason that today's video is so important is that all of those tests that we're going to learn from here on out, and we're going to learn like 8 or 9 different ones, they all fundamentally work the same way. They all follow the same process that we've been talking about in this video. The only difference between them is going to be the number of variables that you have and the types of variables that you have. So if we're testing, for example, for a relationship between 2 continuous variables, we're going to use a different statistic than we would for a relationship between 2 categorical variables, or if we had one of each, for example. That's the only thing that's going to change between these different tests. But they all have one thing in common, which is they're all going to give you that p-value. And remember, that p-value is what tells us whether we think the null hypothesis is correct or whether we think the alternative hypothesis is correct. If we get a p-value that is large, in other words, greater than 0.05, we are going to retain the null hypothesis, and our conclusion in this case would be that there is no relationship between how you take notes and what grade you get on the exam. In other words, there is no difference between students who take notes by hand and students who take notes on a laptop. Now, as we saw a minute ago, we can never be 100% sure that we made the right decision, and we never know. We can be pretty sure, but we can never be 100% sure. If in fact we've made an error here, right? Maybe we failed to find a difference between these groups, but there actually is one, we would say that we committed a type 2 error. The other possible outcome is if we find a very small p-value, a p-value of less than 0.05. In that case, we are going to say that there is strong evidence of a difference or relationship. We're going to reject the null hypothesis, and our conclusion is going to be that there is a significant, notice there's that word again, there is a significant relationship between how you take notes and the grades you get on the exam. In other words, we would say there is a significant difference between the students who took notes by hand and the students who took notes on a laptop. Now again, we can never be 100% sure that we made the right decision. We can be, 99.9% sure in some cases, but we can never be 100% sure. If we made the wrong decision here, we have committed a type 1 error. As I mentioned on Monday, this is a very important video. I very much encourage you to watch it twice if you have the time, because it's very abstract and it lays the foundation for everything we're going to do from here on out. So if you have the time, please watch this video a second time, sleep on it, let it sink in, try to think about it between now and Monday. And if you have any questions whatsoever about anything we've talked about in this video, be sure to bring them with you to class on Monday.